Hello, my name is Martin, and in this video, I'm going to be talking about Deligne-Lusztig theory and character sheaves, two techniques for constructing representations for a particular class of finite groups called finite groups of Lie type. So the plan for the talk is, I'm going to start by giving you some background. What is the problem we're trying to address? What are finite groups of Lie type? And then we're going to take a look at the technique that historically preceded Deligne-Lusztig theory, called parabolic induction, in the hopes that it will motivate some of the constructions we see later. Then we'll move on to Deligne-Lusztig theory. And I am going to give the construction of the Deligne-Lusztig characters, which is the most technical part of this talk. But before I do that, I'm going to try and motivate it a bit more by drawing some analogies with topology and discussing permutation representations a little bit. We'll then give the construction, and we'll conclude the section on Deligne-Lusztig theory by talking about some useful results. What do we get out of doing this? And also a few of the problems that arise. Finally, we'll talk about character sheaves. Now, I'm not going to give the construction of the character sheaves because it's even more technical than the construction of the Deligne-Lusztig characters, but I'll talk about why character sheaves arise, how they help with some of the problems coming from Deligne-Lusztig theory, and we'll conclude by taking a look at how we can recover the Deligne-Lusztig characters from character sheaves. So a big problem in representation theory is finding representations of finite groups. Now that's two broader problems. Let's narrow our focus to finite simple groups. Simple just means there are no non-trivial normal subgroups. You may or may not know that there is a classification of such groups. There are the 27 sporadic groups, the cyclic groups of prime order, the alternating groups, and a collection of families of groups that all fall under the heading finite simple groups of Lie type. So one approach to this problem is to construct the representations of the sporadic groups and the cyclic groups and the alternating groups using ad hoc methods, and then we could try and treat the representations of the finite simple groups of Lie type together. So in this talk, we're going to be interested in understanding the representations of finite groups of Lie type. Well, what is a finite group of Lie type? Let's start by looking at some examples. There's the general linear group over a finite field, the special linear group, the special orthogonal group, the symplectic group. These are the so-called classical finite groups of Lie type. And informally, you can think of a finite group of Lie type as taking a Lie group, that's a group which is also a Euclidean manifold over the real numbers, and plugging in a finite field FQ. Now, I'm about to give the formal definition. It includes a few technical terms that I don't want to define, so if you don't know what they mean, I want you to ignore this and just think of the informal definition. So formally, a finite group of Lie type is the finite group of fixed points of a connected reductive linear algebraic group under a Frobenius endomorphism. So now that we know what finite groups of Lie type are, let's construct some representations by studying the technique which Deligne-Lusztig theory generalizes, called parabolic induction. We've got some setup. G is the general linear group over the algebraic closure of a finite field. B is the subgroup of upper triangular matrices inside G. Now, B is what's known as a Borel subgroup, which I don't want to define, but if I say the word Borel in the rest of the video, you don't know what it means, I want you to think concretely of upper triangular matrices inside G. We've also got the subgroup T of diagonal matrices inside B, which I'm denoting by T because it's what's known as a torus. Again, if you don't know what a torus is, I want you to think of diagonal matrices inside B. The last subgroup is U, the unipotent radical of B. It's upper triangular matrices with ones in the diagonal. And finally, we've got our Frobenius FQ, which raises all the entries in a matrix to the qth power. So we're interested in constructing representations of the finite group GFQ, fixed points under this Frobenius, which turns out to be GLNFQ, the general linear group over the finite field FQ. And what we want to do is take a representation of our torus T and extend it to a representation of G. Those of you who know some representation theory know that there's a way to do this, called induction. But we don't actually want to induce directly from T to G, because in representation theory, we're not just interested in representations, we're interested in irreducible representations, representations that can't be broken down any further. So once we have our induced representation of G, we're going to want to break it down into its irreducible constituents. The problem is that T is much smaller than G. So if we induce directly from T to G, the result is going to be really large. It has a lot of irreducible constituents, and it's hard to decompose. Instead, what we want to do is extend our representation of T to a representation of B and then induce from there. B is much larger than T, and there's less of a jump from B to G, so if we induce from B, the result has fewer irreducible constituents, and it's easier to decompose. Well, how do we actually do this? Every upper triangular matrix can be written uniquely as the product of a diagonal matrix and an upper triangular matrix with ones on the diagonal. That's just saying that B is what's known as a semi-direct product of U and T. And taking fixed points under this Frobenius preserves that semi-direct product. So now what we want to do is take a representation theta of our finite torus TFQ and extend it to a representation of BFQ by letting U of Q act trivially. If you like to think about homomorphisms, we have a surjective homomorphism from BFQ to TFQ coming from the semi-direct product, and we're just precomposing our representation with that surjection. Now we just induce the result from BFQ to GFQ. And that's the procedure of parabolic induction. So the representations that arise this way are what's known as parabolically induced. And there are lots of nice results about parabolically induced representations. It's quite easy to decompose them into their irreducible constituents. So a natural question to ask is every representation parabolically induced? Unfortunately, the answer in general is no. The representations that aren't parabolically induced are what's known as cuspidal. So Deligne-Lusztig theory is introduced to construct the cuspidal representations. The moral of parabolic induction is that characters of TFQ give rise to characters of GFQ, and Deligne-Lusztig theory is interested in the converse. Given a character of GFQ, can we get it from a character of TFQ using some procedure that looks like parabolic induction? As we'll soon see, the answer is yes. In a moment, I'm going to define the Deligne-Lusztig characters, but the construction is quite involved, so before I do, I want to try and motivate it a bit by drawing some analogies with topology and talking about permutation representations. Now, permutation representations are an important technique in the standard representation theory of finite groups for constructing new representations. If my group G acts on a finite set X, I get a representation on the free vector space Cx. Now, the great thing about permutation representations is that the character of a group element G is just the number of points in X fixed by G. So something we might try when we're trying to construct new representations of our finite groups of Lie type is to build an action of GF on a variety and then count the fixed points. A few things can go wrong with that. Maybe our variety is infinite and counting fixed points is hard. So we're going to borrow a result from topology called the Lefschetz-Hopf theorem, which says that if I have a continuous map G from a nice enough space to itself, I can count the points fixed by G by looking at this alternating sum of the traces of the induced maps on singular rational cohomology. Now, there's an analog of singular rational cohomology for varieties called ellatic cohomology with compact support. I don't want to go into it too much, but we can build something that looks like this alternating sum. So our plan for constructing the Deligne-Lusztig characters is to build an action of GF on a variety and then count fixed points by looking at an alternating sum like the Lefschetz-Hopf theorem. All right, we're at last ready to construct the Deligne-Lusztig characters. We again have some setup. So G is a connected reductive linear algebraic group. Think G is GLN FP bar. F is a Frobenius endomorphism of G. T is an F-stable maximal torus, so F-stable just means F of T equals T. B is a Borel subgroup containing T. Think upper triangular matrices containing diagonal matrices. And U is the unipotent radical of B. Think upper triangular matrices with ones on the diagonal. We saw in that particular case that B is a semi-direct product of U and T. And that's actually still true in general. Motivated by the last section, we want to construct a variety that GF acts on, and then we're going to get a character of GF by counting the fixed points of that action. To construct that variety, I'm going to introduce the Lang map, which sends an element G to G inverse F of G. It may not be obvious, but this Lang map is very closely related to the finite group of Lie type GF. For example, the phi bar over 1, well, that's just elements G such that F of G equals G. So the phi bar over 1 is exactly GF. The variety we're going to act on is the preimage of the unipotent radical U under this Lang map, which I've denoted X tilde. The finite group GF cross TF acts on X tilde by left multiplication by elements of GF and right multiplication by elements of TF. Now, having this action on the variety X tilde induces an action on the cohomology. This is ellatic cohomology with compact support, like I mentioned earlier. Now that's exactly a representation of GF cross TF. At this point, we're going to start thinking of representations as modules over the associated group algebra. So each of these vector spaces HKC is a module over the group algebra of GF cross TF, or equivalently, it's a bimodule over CGF and CTF. We can now consider the virtual bimodule, that's the alternating sum of these modules. Now having this virtual bimodule, H upper star, gives us a functor from modules over the group algebra CTF to modules over CGF. Or equivalently, it's a functor from representations of TF to representations of GF. And the functor is just taking a module over CTF and tensoring with the bimodule H upper star. This functor is called Deligne-Lusztig induction. Now I promised we were going to talk about the Deligne-Lusztig characters. Those are just the special case of Deligne-Lusztig induction applied to the irreducible one-dimensional representations theta of TF, and they're denoted RGT theta. Now that construction was quite involved, so let's check we actually get some useful results about the Deligne-Lusztig characters. Firstly, Deligne-Lusztig induction generalizes parabolic induction. If our maximal torus T happens to be contained in an F-stable Borel, so that just means f of b equals b, then RGT theta is the parabolically induced character we constructed earlier. There's an important point here. Every F-stable maximal torus is contained in some Borel, but not every Borel is F-stable. And in particular, it's possible to find F-stable maximal tori that aren't contained in any F-stable Borel subgroup. That's kind of why Deligne-Lusztig induction is exhaustive and parabolic induction isn't. Another important feature is that there is an explicit formula for the values of the virtual characters RGT theta. I'm not going to write it down because it's quite complicated, but it doesn't involve elliptic cohomology. So you don't have to do any hard algebraic geometry to calculate the values of the Deligne-Lusztig characters. The last thing is that, as I said, Deligne-Lusztig induction is exhaustive. Every irreducible representation of GF appears as a constituent of some Deligne-Lusztig character RGT theta. Now the big problem with Deligne-Lusztig induction is that although every irreducible representation appears as a constituent, it's hard to pick them out. I mentioned earlier that there are lots of results for decomposing parabolically induced representations, but those don't generalize to the case of the Deligne-Lusztig characters. So that's where character sheaves enter the picture. What we're going to do is associate to the Deligne-Lusztig characters some objects that have more structure. And then decomposing the character sheaves is going to induce a decomposition of the Deligne-Lusztig characters, which will in turn allow us to recover the irreducible constituents. So how do we construct these character sheaves? Well, hopefully it's not surprising that the idea is to take a nice enough sheaf L on our maximal torus T and extend it to all of G. But how should we extend it? Well, we're hoping to recover the Deligne-Lusztig characters from our extended sheaf. And remember that characters are, in particular, class functions. They're constant on conjugacy classes. So we want our extended sheaf to be, in some sense, invariant under conjugation. So what we're going to do is we're going to take our sheaf L and extend it to all of the conjugates of T by conjugation. Now, it turns out that this union of conjugates of T is dense in G. So we can now extend this conjugated sheaf to a sheaf on G using a process known as intermediate extension. Now, the technical construction of intermediate extension is not so important. What you should think is that the resulting sheaf on G is the closest possible approximation of our conjugated sheaf. And that's it. That's the entire process. We call the result a character sheaf and denote it KLT. Well, that's great. Now we've got some sheaves, but how do we start getting characters back? Notice that nowhere in this construction does the Frobenius F show up. This is actually the first time it appears. If I want to study the Deligne-Lusztig characters on the finite group of Lie type GF, I'm going to restrict my attention to the character sheaves coming from F stable L. F stable just means that F upper star of L is isomorphic to L. Now, normally that isomorphic to wouldn't matter so much, but in this case we actually do need to keep track of the isomorphism. We call a choice of isomorphism from F upper star of L to L a Weil structure, denoted tau. Now, if the element little t happens to be fixed by the Frobenius, then the stalk of f upper star of L at t is the stalk of L at t. So our V structure tau acts on the stalk of L at t. We can therefore define this function chi L tau to just be the trace of the induced map on the stalk. I should say that the stalk of L at t is just a finite dimensional vector space, and this trace is just the ordinary trace of a linear map. Now, a really important theorem is that after normalizing tau so that the induced map on the stalk at the identity is the identity map, chi L tau is a character of TF. And moreover, every character appears as chi L tau for some pair L tau. So hopefully now you can start to see the plan. If I want to study the Deligne-Lusztig character RGT theta, I pick a pair L tau so that theta is chi L tau, and then I'm going to study the character sheaf KLT. But what does study mean? Well, our choice of V structure tau induces an isomorphism from the pullback of the character sheaf to itself. Our character sheaf is also F stable. Now, arguing exactly as in the torus case, tau acts on the stalk at G for any G that's fixed under the Frobenius. We can therefore define this function, called a characteristic function, as the alternating sum of the traces of the induced maps on cohomology. This should look familiar. It's again modeled on the Lefschetz-Hopf formula. So from our character sheaf, we've now recovered a natural function, and the hope would be that this is related to the Deligne-Lusztig characters. It turns out that, up to a sign, this is the Deligne-Lusztig character arising from chi L tau. And that's it. So hopefully now you start to see the connection between the character sheaves and the Deligne-Lusztig characters, and also how powerful a tool this is. Where before we only had information on stalks, now we have information on every open set. In practice, that's what allows us to decompose the character sheaves, which in turn induces a decomposition of the Deligne-Lusztig characters, which is what we were actually interested in. Now, I'm out of time, so I can't say any more about that, but I wanted to finish by saying thank you for watching this video, and I hope you got something out of it.